Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll continue Chapter 5, talking about doing diagnostics on factor models. So here we are in Chapter 5, and I'll bring up the chapter. We have just been doing an analysis on, by page up here, treatments for itching, where we have a block design where we have 10 people. Each person defines a block, and each person has experienced 7 treatments and the imposition of having to undergo itching from cowage. And after doing this analysis, we found that there are, sorry, I'm jumping all around here. We found that there are differences between treatments, but also between blocks, between the patients, which is important because it allows us to observe this treatment effect. In fact, I recommend, just for contrast, remove the patient block here and just do seconds versus treatment and see whether there's differences in treatments. So we're now wanting to see, I'm paging down now, see whether the model assumptions hold. And we're going to do the standard diagnostic analysis of looking at residual and QQ plots to see whether there are influential observations or whether different assumptions are met. Here are those plots, and the first thing to notice, different from multiple regression with continuous explanatory variables or predictor variables, those X variables, is we have categories now. And so in particular, residuals versus treatment, we have 7 treatments. They're not all listed here, but they're in the same order as in tables above. And here they are for patients, patients 1 through 10. And so now we've got summaries which are box plots. And we now need to remember what the assumptions are for our regression models. All of our assumptions are on the residuals, which is why residuals are the things that are plotted here. In particular, residuals should be normally distributed. So we can look at our QQ plot and see whether they're normally distributed. Next, we want to see whether they have constant variance. So the variance should be the same regardless of treatment and regardless of the block or the patient. And we should also not see any structure with the residuals versus the fitted values or anything else. And no observation should be so influential that it dictates the differences that we observe. So let's go back to the normality assumption. Pause for a moment this video, and in your notes, you could probably observe this curvature here. None of the points are outside of the bands, well, maybe observation 52. So 1 out of 70 is not that unusual. You know, what causes that curvature? It's not a major problem here, but how would you fix it? So you paused, you thought about it, you looked up at the data, you came back to the video, here we go. So now I'll give you my thoughts about this. So if I scroll up to the data, our response variable is the duration of itching. It's bounded below by 0, and it goes positive. And this is a standard sort of biological situation we're in, where we have something that, some length, in this case it's a length of time, bounded below by 0, and it gets bigger and bigger. And as we see in many biological situations, we have lots of values sort of closer to 0, and their proximity to each other vertically here is that they're sort of closer to each other at the low ends, and then they spread out as you get larger and larger. And so we have this right skewness. If we were to put this plot on its side and create a histogram, we would see some right skewness. There's longer tails for the large values for itching. And so that right skewness is just a feature of our response. So we may actually consider doing a log transformation of the duration, or some other transformation like square root, and see whether that improves the normality assumption of our residuals. I'll page back down to those model assumptions. So in this case, it's not so grievous that it probably affects our results very much. So this is a judgment call. If you really needed this analysis to be interpretable on the original scale of number of seconds, then you may want to keep this analysis. And in fact, I'll show you in a second what, if you were willing to say, well, this is a violation of normality, you could even do an Anderson-Darling normality test or some numerical hypothesis test for normality and get more evidence that way. But if you want to conclude that this is not normal enough, then there's a non-parametric strategy just below. All right, so let's look at our constant variance assumption. So we'll start by looking across treatments. So we're basically saying, is the variability over these 7 treatments the same? Within each treatment, there's 10 observations. These are the 10 patients. So there's 10 observations here. Is the variance equal? Well, so to the eye, you might be tempted to conclude that the second and the 6th one are much higher in variability than, say, the 3 middle ones. This comes down to experience about knowing how random numbers look when you draw them from a distribution. If we were to assume that the data come from a normal distribution within each of these, so say no drug, and it has some variance, and then draw random samples, and you were to draw 7 random samples from the same distribution, from my experience, you could very easily get 7 samples of 10 observations from the same distribution that look just like this. So for me, the differences I observe here seem to come down to, or I would conclude sort of come down to, just random variability between people. For me, I would need to see much bigger differences with these small sample sizes to conclude something different. Let's look over for residuals by patient. So patient 10 looks like he has the most variability, whereas patient 7 maybe has about the least. Patient 2 has very little variability as well, except for this one treatment that really drove him nuts. That ended up being the placebo. That's observation 20 right here. It has high influence, and yeah, that was the patient 2 under the placebo. So there may be some differences here. Keep in mind that there were only 7 observations in each. So I'm maybe not too impressed about whether there's differences. So I'm feeling okay with these 2 residual plots. Though, because there's 3 things here that are sort of all happening, right? So is there non-constant variance or not? Are these residuals normal? I may want to do what I do below, which is a non-parametric test. All right, let's walk through the rest of these plots. In the top left, we've got residuals versus fitted values. We see that there's basically, this is not bad. We have 3 observations up here that have people who just had a bad time on one of the treatments. Observation 20 is patient 2 under the placebo. There are these 2 others that sort of itched for much longer than you were expecting. This residual of 100 means 100 seconds longer than you expected, up to 150, 2.5 minutes. No, 3 minutes. So 120, 2.5 minutes. Yeah, so these are people who just itched much longer than you expected. Okay, so we've got these 3 Cook's distances. We can think about whether we want to exclude these or not, and see whether that affects the significance of the regression contrasts. For example, when we saw that the PAP-V versus the placebo were different, the mean for the placebo, if I scroll up to the original data, or the plot of the data, rats. Okay, so remember this is one big outlier up here at the top. And so this mean for the placebo is being drawn up because of that extreme observation. PAP-V is the smallest mean. It's also being drawn up by this extreme observation. But that's the biggest contrast. It's also, PAP-V is also being drawn down by this person who stopped itching after, gosh, less than a minute. Lucky. So those are some of the influence. Here's the 2 other observations that stick out from the that have that high Cook's distance. This last one for the tripel is the same, looks like the same as this person up here. This gold is a different shade gold than this orange. Anyway, so maybe the difference is partly due to the strong influence of observation 20, which was sort of an outlier in that vertical direction. So the last thing I want to point out is the leverage plot. So leverage is basically useless as a measure when there's no continuous variables, when everything is a factor. So here, treatments are factors, patients are factors. And so the leverage tells you how much of an outlier an observation is in the x direction, so in the direction of your predictor variables. Well, in this case, notice that all the points are in the same place. And that's because there's no real center here. Everything's a category. It's not that no drug is further out than amino, right? These are 7 different categories. There's no ordering. So they're all just as far from some hypothetical center as any other condition. Similarly, all these patients are different categories, and so they're all equal distance. And so this number, 0.228, etc., is just some number that is the same for every observation. So this plot is not going to be give us any information here. We really just care about the vertical distance in this case, which is the Cook's distance, which is on this middle plot, which is broken out by observation numbers. So this is really the plot we care about. All right. So we can either go with the I think for this for this experiment, if this was my data, I would redo this analysis by taking the log transformation to improve the normality of the residuals, take off this curve, and see how things change. The interpretation obviously being on the log scale instead of the natural scale for seconds. The other thing we can do, as I scroll down, is the nonparametric version of the tests. So the nonparametric version is going to be the same, except we no longer assume that the residuals are normal. So that's called the Freedman Test, and this is one way to do that. So we're interested in testing whether treatments are different conditional on patients or by patient. So this is a way of controlling for the patient effect and asking whether treatments differ. And here we get a chi-square statistic and a degrees of freedom, and this says, yes, there are differences here between treatments. And then you'd need to do a follow-up here to ask which pairs are different. All right. Come on back, and we will put our blocks aside and look at how to extend this to having multiple factors. And we'll look at an experiment where we've got 2 factors and then start asking things about interaction. So this is where things start getting really interesting.